Alright, now I want to talk about part B of the lab, density lab. In this case, you're also going to calculate density of liquid, and it happens to be a soda in this case, so you're going to calculate the density of Coca-Cola as well as Diet Coke. The method to do this is actually quite straightforward. You're going to set up a burette and you're going to fill it up with Coca-Cola or Diet Coke. So when you fill it up with Coca-Cola, basically what you're going to do is use the burette to deliver approximately 5 milliliters of Coke into that beaker. Now, the actual volume that you deliver, you're going to have to read by using the burette, right? And then you're going to weigh how much of the Coca-Cola you actually deliver into the beaker. And you can do this by weighing by difference, which is by weighing the empty beaker first and then weighing the beaker with the Coke. And after you have the mass and the volume, you can calculate the density. Now, after you do that, you're going to add another 5 milliliter of Coke into that same beaker. So now roughly you're going to have 10 milliliters. Again, the actual volume will be dependent on what you read on the burette. And then you're going to weigh that new beaker again, figure out the mass, calculate the density again. And you repeat this 6 times for the Coke, and you do the same repetition with the Diet Coke six times as well. Now the key here is to remember that density would, every time you're going to calculate the density using the total mass over the total volume. Okay, so understand that you're going to deliver about 5 milliliters every time to the beaker, but then the total mass and the total volume will be different, right? Because you're increasing the mass by adding more and more Coke to your beaker. So then your volume will be larger, your mass will be larger. So you're going to calculate the density using those numbers, the total numbers. Okay? There's a reason to do this. And in fact, you're going to be asked why you do that in the lab report, one of the questions in the lab report. So you might want to think about a little bit why we use, in this case, total values, total mass versus total volume. What are we trying to show here by measuring this density quantity with total mass and total volume? And think about it. What would happen to the density value as you calculate it from the first measurement all the way to the sixth measurement? Will it change? Will it not change? And one way or the other, can you conclude what type of property density is? All right, now I want to talk about the last part of this lab, which is part C. Here you're going to be calculating the density of an unknown metal, okay? Now, density is a useful property to have because a particular metal would have that specific density. So whether I have a little bit of gold or a lot of gold, right, the density of that gold would always be 19.3 grams per cubic centimeter. So if I want to identify a piece of metal to be gold, what I need to do is just measure the density or calculate the density of that particular metal, and it happens to be 19.3. That tells me that, well, that's probably gold. So that's exactly what you're going to be doing in this lab. You're going to be given, each group is going to be given an unknown metal that has a code on it. Now you have to write down this code, and basically your goal is to figure out what is that metal, okay? Now the metal, you have a selection of metals that you can have. This was an old set of selection. In your lab report, it would list what the selection will be, okay? But these are some of the metals we used to use. So what you have to figure out is, well, which of these metals is the one that's going to be in my vial? And again, you're going to have to take a look at your lab manual itself to see what selection of metals you're going to have this time around. Okay, now let's talk a little bit about the way we're going to find this density of the metal. Okay, now as I said before, any density is always the mass of that substance divided by the volume of the substance. In this case, we happen to be dealing with a metal. We want the mass of the metal divided by the volume of the metal. Now we're going to use the vials, these vials that you're given. There's going to be another set of vials that you're going to do the experiment in, but they look identical. So we're going to use these vials basically to determine the mass and the volume of the metal. And the method is a little complicated for the volume, so you should listen carefully when we get to that point. I'm going to take you slowly, but let's talk a little bit about the mass, okay? Mass of the metal is really fairly easily determined, right? You can just do that measuring by difference, where you measure the empty vial first, and then you put some metals in it, and you measure the difference of the masses between those two. That should correspond to the mass of the metal. Now let's think a little bit about how to measure the volume now. Okay, so what I want is just the amount of space taken up by the red metals here, right? All these little pieces of metals. I want to know exactly how much volume they're taking. I can't calculate this number because it's kind of all these metals have different shapes and sizes, so it's not possible for me to calculate the actual volume. I have to actually measure it. I'm going to measure it the following way, okay? If you think about the empty vial right here, think about what's filling up that space right now, okay? Now, if you think a little bit about it, it's really air that's filling up that empty space, right? It's not a completely empty space, there's air in it, okay? So the volume of air in that vial is the same as the volume of the vial. Now, in this vial, okay, the volume of the vial is equal to what? If you think about it, it should equal to the volume of the air in the vial plus the volume of the metal in the vial. So in other words, the metal takes up some space, air takes up the rest of the space. So the volume of the vial in this case is going to be the sum of the volume of the metal plus the volume of the air in this vial, okay? And that's a really useful concept to keep in mind. The volume of any space is really equal to the sum of the volume of individual components that fill that space. In this case, in the empty case, we only have air, so the volume of the vial is the same as the volume of air. In the case where we fill it up with some metals, the volume of the vial is equal to the volume of the metal plus the volume of the air that occupies that vial.